Imagine being born in a prison you can never leave. You'll live your entire life inside metal walls, breathing recycled air and never touching Earth because Earth is already dead to you. This is a generation ship. How do you keep humans alive for centuries in the void without going extinct? If you want more mind-bending space mysteries like this, hit subscribe. You don't want to miss what's coming next. Now let's begin. Let's start with the most basic question. Where would we go? Our nearest stellar neighbor is Proxima Centauri, a small red dwarf star located 4.24 light-years away. That might sound close in cosmic terms, and honestly, it is. In a universe measured in billions of light-years, Proxima Centauri is practically next door. But here's the reality check. Even traveling at 10% the speed of light, which is wildly optimistic with our current technology, the journey would take over 40 years. And 10% light speed, that's roughly 30,000 kilometers per second. We've never built anything remotely close to that velocity. The fastest human-made object right now is the Parker Solar Probe, which reached speeds around 192 kilometers per second during its close approach to the Sun. That sounds impressive until you realize it's only about 0.064% the speed of light. At that pace, reaching Proxima Centauri would take over 6,000 years, 6 millennia. The entire span of recorded human civilization, from the earliest Sumerian cities to today, would unfold aboard that vessel before arrival. This is why we're talking about generation ships. If we can't achieve near-light speeds, and there's no evidence yet that we can, then interstellar travel becomes a multi-generational endeavor by necessity. You don't pack for a weekend trip. You pack for the continuation of human civilization itself. And that raises an extraordinary question. Can we actually build a closed system capable of sustaining human life for centuries, or even millennia, without resupply from Earth? To understand the challenge, let's look at what we know about closed life support systems. The International Space Station, our most advanced long-duration spacecraft, isn't remotely closed. It relies on regular resupply missions from Earth, bringing fresh water, food, oxygen, spare parts, and even clean clothes. Astronauts recycle some resources, yes. The environmental control and life support system recovers about 93% of water from urine and humidity, which is remarkable, but the station still loses resources constantly. Water molecules escape during airlock operations. Oxygen is lost when cargo ships depart. Food cannot be grown in sufficient quantities on board. The ISS is a leaky system by design because it doesn't need to be perfectly closed. Earth is only a few hundred kilometers below. A generation ship has no such luxury. Once you leave Earth's orbit and begin accelerating toward another star system, there is no coming back. There are no resupply missions. Every molecule of water, every breath of oxygen, every calorie of food must either be brought along or regenerated from waste. You're creating a miniature Earth, a completely self-sustaining biosphere, and keeping it running for longer than most nations have existed. Scientists have tried to build closed ecosystems before. The most famous attempt was Biosphere 2, a 3.14-acre structure in Arizona designed in the late 20th century to simulate a sealed ecological system. The experiment ran from 1991 to 1993 with 8 people living inside. It failed. Oxygen levels dropped dangerously low because soil microbes consumed it faster than plants could produce it. Carbon dioxide fluctuated wildly. 19 of 25 vertebrate species went extinct. Cockroaches and ants exploded in population. The psychological stress on the crew became severe, with factions forming and conflicts escalating. And this was on Earth, with the entire planet's resources just outside the glass, with emergency intervention possible at any moment. Now imagine that same system, but in deep space, with cosmic radiation sleeting through the hull, no possibility of outside help, and the pressure of knowing that failure means the extinction of everyone aboard. The stakes couldn't be higher. But here's where it gets fascinating. Despite Biosphere 2's failure, we've learned an enormous amount about closed-loop life support. The European Space Agency's Melissa project, which stands for Micro-Ecological Life Support System Alternative, has been developing bioregenerative systems since 1989. Melissa uses bacteria, algae, and plants in a connected loop to recycle waste into usable resources. Human waste and carbon dioxide go in. Oxygen, water, and potentially food come out. It's a microbial solution inspired by natural ecosystems, and early results are promising. Small-scale demonstrations have successfully closed various loops, proving the concept works in principle. Research published in Frontiers in Astronomy and Space Sciences in 2023 presented stoichiometric models for fully closed bioregenerative life support systems. These mathematical models account for every atom of carbon, nitrogen, oxygen, and hydrogen cycling through the system. They calculate exactly how much plant biomass you need to support a given number of humans, how much waste those humans produce, how much energy is required to keep everything running, and where the system might fail. The models suggest that with current technology we could theoretically create a closed system, but the margin for error is razor-thin. Any significant imbalance, any unexpected die-off in your algae tanks or crop failure in your hydroponic farms could cascade into catastrophic system failure. And we haven't even talked about the ship itself yet. How big would it need to be? What shape should it take? These aren't arbitrary questions. The architecture of a generation ship is dictated entirely by the biological needs of its population. A study by astrophysicist Frederick Marin and his colleagues used a sophisticated numerical code called Heritage. Heritage stands for a complex agent-based Monte Carlo simulation to calculate resource requirements for multi-generational space voyages. Their findings are sobering, but here's where theory meets reality. Building such a system is one thing, keeping it stable for centuries is another. Ecosystems are notoriously fragile. A single pathogen, a nutrient imbalance, or an unexpected die-off of a key species could trigger a cascade that collapses the entire food web. On Earth, we have the luxury of biodiversity. If one crop fails, we have alternatives. If a disease strikes, the ecosystem adapts. A generation ship wouldn't have that buffer. Every organism aboard would need to be carefully selected, monitored, and managed. Researchers studying closed-loop biospheres have learned harsh lessons from experiments like Biosphere 2, a facility built in Arizona in the 1990s. It was designed to be a self-contained ecosystem, supporting 8 people for 2 years. Despite meticulous planning, the experiment faced numerous problems. Oxygen levels dropped unexpectedly as microbes in the soil consumed more than anticipated. Carbon dioxide spiked. Certain species thrived while others died off, disrupting the intended balance. The crew eventually needed external intervention to survive, and that was just 2 years with 8 people. Imagine the complexity of sustaining 1,000 people for multiple centuries. Space agencies and research institutions are acutely aware of these challenges. The European Melissa project, which stands for Micro-Ecological Life Support System Alternative, has been working since the 1980s to develop fully closed bioregenerative systems. Their approach involves 5 interconnected compartments, each hosting specific organisms and chemical processes. The first compartment breaks down waste into simpler compounds using anaerobic bacteria. The second oxidizes those compounds. The third uses photosynthetic bacteria to capture carbon dioxide. The fourth grows higher plants for food and oxygen. The fifth houses the crew. Every element is connected in a circular flow, with waste from one stage becoming the input for the next. It's biomimicry at its finest, replicating the way Earth's biosphere functions, but in miniature. Recent models published in Frontiers in Astronomy and Space Sciences in 2023 show that a fully closed Melissa-style system could theoretically sustain a crew indefinitely, assuming no catastrophic failures. But the key word there is theoretically. Testing such systems in the harsh environment of deep space remains a formidable challenge. Let's shift gears for a moment and talk about energy, because nothing aboard a generation ship works without power. Lights for crops, pumps for water, computers for navigation, life support systems, communication arrays, and manufacturing equipment all demand energy. Where does it come from? Solar power, so abundant near Earth, becomes useless once a ship ventures beyond the orbit of Mars. The sun's light weakens with distance, following an inverse square law. By the time a generation ship reaches the outer edges of the solar system, solar panels would be practically worthless. Nuclear power is the most viable option. Fission reactors, similar to those used in submarines and some spacecraft, could provide steady, long-term power. But uranium or plutonium fuel has a finite lifespan. Even with advanced breeder reactors that produce more fuel than they consume, the supply would eventually run out over centuries. Fusion reactors, which fuse hydrogen isotopes to release energy, offer a more promising solution. If humanity can master fusion technology, a generation ship could carry deuterium or helium-3, fuels abundant enough to last for extremely long voyages. Unfortunately, despite decades of research, controlled fusion remains elusive. Projects like ITER, the International Thermonuclear Experimental Reactor, aim to demonstrate net positive fusion energy by the 2030s, but scaling that technology for a starship is another matter entirely. Some futurists propose antimatter propulsion, which would provide both thrust and energy. When matter and antimatter collide, they annihilate each other, releasing enormous amounts of energy. But producing and storing antimatter is extraordinarily difficult and expensive. Current production rates are measured in nanograms per year. Powering a generation ship with antimatter would require breakthroughs far beyond our present capabilities. Even if we solve energy, food, water, and radiation, we still face a problem that's perhaps the most human of all: psychology. Living in a confined space for your entire life, knowing you'll never see Earth, never breathe open air, never experience the freedom of a natural world, takes a psychological toll that's difficult to overstate. Astronauts on the International Space Station sometimes struggle with isolation and confinement, and they know they're going home in 6 months. Imagine never going home, ever. Studies on isolated environments such as Antarctic research stations and long-duration submarine missions show that people can adapt to confinement, but they need certain conditions. Social structures must be stable. There must be meaningful work, opportunities for recreation, and ways to maintain mental health. Privacy is crucial. On a generation ship, every individual would live in close quarters with the same people or their descendants for their entire lives. Conflicts, once ignited, could fester for generations. Sociologists studying generation ship feasibility emphasize the need for governance structures, conflict resolution systems, and cultural continuity. How do you maintain a sense of purpose when the goal is generations away? How do you prevent stagnation or social collapse? One fascinating aspect is the role of culture and education. Each generation must be raised to understand the mission, to value the long-term goal, and to maintain the knowledge necessary to operate the ship. Loss of technical knowledge could be catastrophic. Imagine a critical system failing and no one aboard remembering how to fix it because the information was lost or forgotten over time. This is why redundancy, both in systems and in knowledge, is essential. Some researchers propose digital archives, constantly updated and accessible to all crew members. Others suggest a culture of apprenticeship, where skills are passed down directly from one generation to the next. Either way, education becomes a matter of survival. Speaking of survival, let's not forget the engineering challenges of the ship itself. A generation ship would be the most complex machine ever built. It would need to function flawlessly for centuries with minimal outside intervention. Components would wear out, requiring maintenance and replacement. This means the ship must carry manufacturing capabilities, including 3D printers, machine shops, and raw materials. But even raw materials are finite. Over time, entropy takes its toll. Systems degrade, materials fatigue, and accidents happen. A recent study using the Monte Carlo code FLUCA simulated radiological impacts during long-duration space missions, including journeys to Mars, Europa, and even interstellar space. The findings were sobering. A transit to Mars alone would expose crew members to approximately 300 millisieverts of radiation, even with shielding. For a journey to the outer solar system or beyond, the cumulative dose over decades or centuries could far exceed safe limits, requiring advanced shielding technologies we haven't yet developed. Now you might be wondering, with all these challenges, is a generation ship even feasible? The answer is complicated. From a purely engineering standpoint, yes, it's possible, but it would require technologies at the cutting edge of what we can currently achieve, and some that we haven't mastered yet. From a financial and political standpoint, the obstacles are even greater. Building a generation ship would cost trillions of dollars, require international cooperation on an unprecedented scale, and demand a level of long-term commitment that modern societies have rarely demonstrated. But here's the thing, humanity has always been driven by exploration. We've crossed oceans, climbed mountains, and ventured into space, often against overwhelming odds. The generation ship is the next frontier, the ultimate expression of our desire to reach beyond ourselves. If you're fascinated by these cosmic questions, you might also enjoy my video on why galaxies are mostly empty when they have billions of stars. It explores the incredible vastness of space and how the structure of galaxies reveals deep truths about the universe. You'll find it linked in the description and in the card above. Trust me, it's a journey worth taking. Let's dive deeper into the mechanics of keeping a generation ship running for centuries. One of the most overlooked challenges is the maintenance of genetic diversity. A small population, isolated for many generations, faces the risk of inbreeding, genetic drift, and the accumulation of harmful mutations. Population geneticists recommend a minimum viable population of several thousand individuals to maintain genetic health over the long term. But carrying thousands of people requires a ship exponentially larger, heavier, and more expensive. Some scientists propose alternatives, such as carrying frozen embryos or genetic material that could be used to increase diversity when needed. Others suggest periodic genetic screening and careful management of reproduction to minimize risks. These are uncomfortable topics, raising ethical questions about reproductive freedom and eugenics, but they're unavoidable when planning a multi-generational voyage. Another underappreciated issue is propulsion. Getting a massive generation ship up to a significant fraction of light speed is no small feat. Conventional chemical rockets are far too inefficient. Even nuclear propulsion, while more powerful, struggles with the sheer mass involved. The most promising concepts involve advanced propulsion systems like ion drives, which provide continuous low thrust over long periods, or even more speculative ideas like fusion or antimatter engines. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, proposed a two-stage fusion rocket capable of reaching 12% the speed of light. The design was never built, but it demonstrated that interstellar travel, while difficult, is not impossible. More recently, Breakthrough Starshot, an initiative funded by tech billionaires, aims to send tiny probes to Alpha Centauri using laser propulsion. While these probes are unmanned and far smaller than a generation ship, the technology could inform future designs. Imagine a massive laser array in space pushing a generation ship to high speeds by striking a vast sail. It's ambitious, perhaps even audacious, but it's within the realm of possibility. Micrometeorites and space debris pose another constant threat. At high speeds, even a grain of sand carries enormous kinetic energy. A collision with a micrometeorite could puncture the hull, depressurize sections of the ship, or damage critical systems. To mitigate this, generation ships would likely incorporate multiple layers of shielding, including Whipple shields, which are spaced layers designed to vaporize incoming particles before they reach the hull. Advanced sensors would detect larger objects, allowing the ship to maneuver around them. But space is vast, and not every threat can be anticipated. Redundancy and compartmentalization become essential. If one section is compromised, it must be sealed off without jeopardizing the rest of the ship. Communication is another fascinating aspect that often gets overlooked. Once a generation ship travels beyond a few light years from Earth, real-time communication becomes impossible. Even at the speed of light, messages would take years to reach their destination. A ship 4 light-years away, near Proxima Centauri, would experience an 8-year round-trip delay for any conversation with Earth. After a decade of travel, the crew would essentially be on their own, making decisions without guidance from mission control. This isolation has profound implications. The crew must be self-sufficient, not just physically, but intellectually and culturally. They can't rely on Earth for technical support, medical advice, or even moral guidance. They become, in effect, an independent civilization. This raises fascinating questions about identity and belonging. Would the crew still consider themselves human, or would they develop a distinct identity as starfarers? Would they maintain loyalty to Earth, or would new allegiances emerge? Let's talk about the ship's design in more concrete terms. Most generation ship concepts envision a rotating cylinder or torus to create artificial gravity through centrifugal force. The O'Neill cylinder, proposed by physicist Gerard O'Neill in 1976, remains one of the most detailed designs. Picture a cylinder 20 miles long and 4 miles in diameter, rotating once every 2 minutes. The rotation creates Earth-normal gravity on the inner surface, where people would live. The interior could be landscaped with parks, forests, lakes, and agricultural zones, providing both psychological comfort and practical resources. Windows running the length of the cylinder would let in sunlight reflected by external mirrors. The entire structure would be a world unto itself, capable of supporting tens of thousands of people. Building such a structure would require millions of tons of material, likely sourced from asteroids or the Moon, to avoid the massive cost of launching from Earth's surface. Advanced robotics and autonomous manufacturing would be essential, as would decades of construction time. It's a multi-generational project just to build the ship, let alone to fly it. The Stanford Torus, another classic design from the same era, is a rotating wheel about 1 mile in diameter. The habitable area is along the outer rim, where rotation creates gravity. The center serves as a docking port and zero-gravity work area. While smaller than an O'Neill cylinder, a torus is structurally simpler and might be easier to build with near-term technology. The trade-off is reduced living space and a smaller population capacity, which increases genetic risks over long voyages. Engineers must balance these competing factors when designing a viable generation ship. Radiation shielding deserves more attention because it's one of the most critical and difficult problems. Cosmic rays, particularly galactic cosmic rays, are high-energy particles that permeate space. They originate from supernovae, neutron stars, and other violent cosmic events. Unlike solar radiation, which comes primarily from the Sun and can be shielded relatively easily, galactic cosmic rays come from all directions and penetrate deeply. A paper published in the European Physical Journal Plus in 2026 reviewed radiation risks for deep space exploration. The study found that even with 10 centimeters of aluminum shielding, which is substantial, astronauts would receive radiation doses far exceeding safe limits during a multi-year journey. Aluminum actually makes some aspects worse because high-energy particles striking aluminum nuclei can produce showers of secondary particles, increasing exposure rather than decreasing it. Better shielding materials include water, polyethylene, and other hydrogen-rich substances that absorb radiation without creating as many secondary particles. Some generation ship designs propose embedding water tanks within the hull, surrounding living areas with several meters of water. This serves triple duty: radiation shielding, water storage, and thermal regulation. Other designs suggest using regolith, the loose rock and dust found on asteroids and moons, as bulk shielding. A layer of regolith several meters thick would provide excellent protection, though it adds tremendous mass. Still, other concepts involve active shielding, using magnetic or electrostatic fields to deflect charged particles. While this sounds like science fiction, it's based on real physics. Earth's magnetic field does exactly this, protecting us from solar wind and cosmic rays. Generating a similar field around a spacecraft is theoretically possible, but would require enormous amounts of energy and superconducting magnets. Research into plasma shields and mini-magnetospheres is ongoing, with small-scale experiments showing promise. Whether this technology can be scaled to protect an entire generation ship remains an open question. Even with perfect shielding, some radiation gets through. This leads to increased cancer risk, accelerated aging, and potential genetic damage. Studies using the Heritage Code, developed by researchers at the University of Strasbourg, incorporated radiation effects into population simulations. They found that mutations from cosmic rays would accumulate over generations, potentially leading to increased rates of genetic disorders. Natural selection would eliminate the most harmful mutations, but only if they affected reproduction. Mutations that manifest late in life would persist and spread through the population. Managing this requires either accepting higher disease rates or implementing some form of genetic screening and intervention. Neither option is ideal from an ethical standpoint, but biology doesn't care about ethics. The question isn't whether we like the choices, but whether we're willing to make them. Population genetics brings up another critical issue: minimum viable population size. Small populations are vulnerable to inbreeding depression, where mating between relatives increases the frequency of harmful recessive genes. They're also subject to genetic drift, where random chance causes certain genes to become more or less common regardless of their benefit or harm. Over many generations, drift can reduce genetic diversity, making the population less adaptable and more vulnerable to disease. Studies suggest that a minimum of around 500 individuals is necessary to avoid short-term inbreeding, but for long-term stability over centuries, you'd want several thousand. The exact number depends on generation time, reproduction rates, and how strictly you can manage mating patterns. A paper published in Archive in 2021 modeled genetic evolution in multi-generational space populations. The researchers found that with a starting population of around 100 people, genetic diversity would decline significantly within just a few generations. With 500, the population could remain stable, but only with careful management. With 1,000 or more, the risks decreased substantially. This has direct implications for ship size, resource requirements, and mission feasibility. Larger populations are safer genetically but require proportionally larger ships, which are harder to build and accelerate. Social structure becomes another major consideration. How do you govern a society aboard a generation ship? Democracy, authoritarianism, technocracy, each has advantages and drawbacks. Democratic systems allow for representation and flexibility, but they can also lead to conflict and inefficiency. Authoritarian systems provide clear direction and order, but they risk becoming oppressive, potentially leading to resentment and rebellion. Technocratic systems, where experts make decisions based on knowledge and data, might be ideal for a highly technical environment, but they can lack popular legitimacy. Some researchers propose hybrid models where technical decisions are made by experts, but broader social and ethical questions are decided democratically. Others suggest rotating leadership, term limits, and built-in mechanisms for peaceful transition of power. The key is sustainability. Whatever system is chosen must function not just for one generation, but for dozens. It must adapt to changing circumstances without collapsing into chaos or tyranny. Cultural transmission is equally vital. Each generation must be educated to understand the mission, operate the ship, and maintain social cohesion. Knowledge must be preserved and passed down. Imagine a scenario where a critical system fails and no one alive remembers how to repair it because the information was lost or the skill wasn't taught. This is a real risk over centuries. To mitigate it, generation ships would likely maintain extensive digital archives backed up redundantly across multiple systems. But digital storage has its own vulnerabilities. Data degrades, hardware fails, and formats become obsolete. Anyone who's tried to open a file from 20 years ago on modern software understands this problem. Now imagine trying to maintain data integrity for 200 years. Physical books and manuals provide redundancy, but they're bulky and also degrade over time. Oral traditions, apprenticeships, and hands-on training ensure that practical skills are passed directly from person to person. A multi-layered approach combining digital, physical, and experiential knowledge transmission would be essential. Religion and philosophy would play interesting roles aboard a generation ship. Humans have always sought meaning and purpose, especially in difficult circumstances. A voyage spanning multiple generations with no tangible goal visible in any individual's lifetime could be psychologically crushing without some framework to provide meaning. Some crew members might find purpose in the mission itself, viewing it as a sacred duty to carry humanity to the stars. Others might develop new religious or philosophical traditions, blending elements from Earth's cultures with the unique experiences of life aboard the ship. History shows that belief systems evolve over time, sometimes dramatically. Would the original mission remain the unifying purpose, or would new worldviews emerge that prioritize different values? What happens if a generation decides they no longer support the mission and wants to turn back, or change course, or settle somewhere other than the planned destination? These aren't just hypothetical questions, they're genuine risks that mission planners must consider. Psychology and mental health would require constant attention. Depression, anxiety, and other mental health issues are common on Earth, even with access to nature, variety, and freedom. Confine people to a limited space for their entire lives, and those issues could intensify. The ship would need trained psychologists, therapists, and mental health resources. But here's a challenge. Mental health treatment is deeply cultural. Approaches that work in one society might not work in another. Over generations, as the ship's culture evolves, mental health practices would need to evolve as well. There's also the question of neurodivergence. Conditions like autism, ADHD, and others are part of human diversity. How would a generation ship accommodate neurodivergent individuals? Would there be space for different cognitive styles and needs? Or would the pressure for conformity and efficiency marginalize those who think differently? These questions touch on fundamental values about what kind of society we want to create. Conflict resolution is another critical system. Wherever humans gather, conflicts arise. Differences in personality, values, goals, and simple misunderstandings lead to disputes. On Earth, people can move away from each other, change communities, or seek external mediation. On a generation ship, you're stuck with the same people, or their descendants, forever. Minor conflicts can escalate into feuds that last generations. Effective conflict resolution mechanisms, whether through mediation, arbitration, or restorative justice, would be absolutely essential. Some researchers propose training everyone aboard in conflict resolution skills, making it a core part of education. Others suggest professional mediators and clear legal frameworks. The key is preventing conflicts from escalating into violence or social breakdown. One violent incident, one murder, one assault could shatter the fragile social cohesion that holds the community together. Now let's address something that sounds mundane, but is actually critical: waste management. Humans produce waste, a lot of it. Feces, urine, sweat, dead skin, hair, food scraps, broken equipment, worn-out clothing. All of it must be processed and, ideally, recycled. On Earth, we flush toilets and throw away trash, and nature eventually decomposes it. On a generation ship, there is no way. Everything stays aboard unless you jettison it into space, which wastes precious matter. Advanced recycling systems must break down organic waste into base components that can be reused. Human waste, for example, contains nitrogen, phosphorus, and other nutrients essential for plant growth. Properly processed, it becomes fertilizer for crops. Urine can be converted into water and salts. Even carbon dioxide from respiration can be captured and used by plants to produce oxygen and biomass. The Melissa system, developed by the European Space Agency, is designed around exactly these principles. Each waste stream becomes an input for another process, creating a closed loop. In practice, no system is perfectly closed. Small losses are inevitable, escaping during airlocks, binding to surfaces, or being metabolized in ways that aren't easily recovered. Over decades or centuries, these losses accumulate. A generation ship would need some buffer, some reserve of critical elements like nitrogen, phosphorus, and trace metals to compensate for these losses. How much buffer is enough? That's a difficult calculation, dependent on the efficiency of recycling systems and the duration of the voyage. Manufacturing and repair capabilities are equally essential. Systems break, components wear out, accidents happen. The ship must be able to manufacture replacement parts, tools, and equipment. This means carrying raw materials, or better yet, recycling old components into new ones. 3D printing, also known as additive manufacturing, is a promising technology for this purpose. Modern 3D printers can create complex parts from metals, plastics, ceramics, and even biological materials. Aboard a generation ship, printers could produce everything from spare bolts to replacement organs for medical procedures. But printers themselves need maintenance. They have moving parts, electronics, and software that can fail. So you need the ability to repair the printers, which means machine shops, trained technicians, and a supply of spare parts for the printers themselves. It's a recursive problem, and at some point, you need redundancy. Multiple printers, multiple machine shops, multiple people trained in each skill. The ship must be self-sufficient not just in food and water, but in all aspects of technology and infrastructure. Energy storage is another often overlooked challenge. Power generation might come from nuclear reactors, but demand fluctuates. Crops need light during their growing cycle, but not constantly. Life support systems have variable loads. Manufacturing might require bursts of high power. Energy storage systems like batteries or flywheels would smooth out these variations, but batteries degrade over time, losing capacity through repeated charge and discharge cycles. Over centuries, they'd need to be replaced or refurbished. This ties back into manufacturing capability. The ship must be able to produce new batteries or whatever energy storage technology it uses from available materials. The question of children is particularly poignant. On a generation ship, children aren't just the future, they're the mission. Without reproduction, the population dies off and the mission fails. But childhood aboard a ship would be unlike anything on Earth. Children would grow up surrounded by machinery, artificial environments, and a constant awareness of the ship's fragility. They'd be educated from an early age about their role in maintaining systems, growing food, and eventually having children of their own. Would they have a real childhood with play, exploration, and freedom? Or would they be pressed into service as soon as they were capable? Striking the right balance between preparing children for their responsibilities and allowing them to develop as healthy individuals is crucial. Research on Earth shows that childhood experiences profoundly shape adult psychology and behavior. Overly strict or authoritarian childhoods can lead to rebellion or psychological damage. Overly permissive childhoods might fail to instill the discipline and skills necessary for survival. Generation ships would need educators, child psychologists, and social structures that nurture well-adjusted, competent adults. Adolescence would be particularly challenging. Teenagers naturally push boundaries, seek independence, and question authority. On Earth, this sometimes leads to risky behavior, but the consequences are usually limited. On a generation ship where every system is critical and failure means death, teenage rebellion could be catastrophic. Imagine a teenager deciding to hack into environmental controls as a prank or to impress peers, or refusing to follow safety protocols because they resent authority. These aren't abstract concerns. They're predictable aspects of human development. Managing them requires a social structure that channels adolescent energy and rebellion into constructive outlets while maintaining safety and order. Some researchers suggest involving teenagers in meaningful work and decision-making, giving them real responsibility and a stake in the mission's success. Others propose rigorous education and cultural indoctrination to instill a sense of duty. Again, there's a tension between freedom and control, between individuality and collective survival. Let's take a moment to appreciate the sheer ambition of what we're discussing. A generation ship would be the most complex, long-lasting, and ambitious project in human history. It would make the pyramids look like sandcastles and the Apollo program look like a practice run. It would require the cooperation of nations, the dedication of millions of people on Earth to build and support, and the courage of those aboard to carry it forward across generations. It's the ultimate test of humanity's ingenuity, determination, and wisdom. And yet, it's not just about engineering or logistics. It's about what it means to be human. It's about legacy, sacrifice, hope, and the belief that the future is worth investing in, even if we won't live to see it. Now, let's dive deeper into propulsion systems, because how you move a generation ship through space fundamentally shapes every other aspect of the mission. We've already mentioned that chemical rockets are completely inadequate for interstellar travel. They're fine for getting off Earth or maneuvering within a solar system, but they can't achieve the velocities needed to reach other stars in reasonable timeframes. So what are the alternatives? Nuclear pulse propulsion, specifically the Orion concept developed in the late 1950s and early 1960s, involves detonating nuclear bombs behind the spacecraft. Each explosion pushes against a massive shock absorber plate, propelling the ship forward. It sounds insane, and in many ways it is, but the physics actually works. Physicist Freeman Dyson and others calculated that a nuclear pulse ship could reach speeds of several % of light speed, making journeys to nearby stars feasible within a century or two. The challenges are enormous. You need thousands of nuclear devices, each detonating at precisely the right moment and distance. The shock absorber system must withstand repeated nuclear explosions without failing. The radiation from the explosions must be managed both for the crew and to avoid irradiating everything in the vicinity. Environmental and political concerns around launching a ship loaded with nuclear weapons are significant. The Partial Test Ban Treaty of 1963 effectively ended research into Orion by prohibiting nuclear explosions in space, though the underlying physics remains valid. Project Daedalus, designed by the British Interstellar Society in the 1970s, proposed a different approach using nuclear fusion. Instead of fission bombs, Daedalus would use pellets of deuterium and helium-3, ignited by electron beams in a reaction chamber. The fusion reactions would produce thrust, propelling the ship to 12% of light speed. At that velocity, Daedalus could reach Barnard's star, approximately 6 light-years away, in about 50 years. The design called for a two-stage vehicle, with the first stage providing initial acceleration and then being jettisoned to reduce mass. One major challenge is helium-3, which is extremely rare on Earth but relatively abundant on the Moon and in the atmospheres of gas giants like Jupiter. Mining helium-3 would require substantial infrastructure in space, adding to the project's complexity and cost. Daedalus was designed as an unmanned probe, but the principles could be scaled up for a crewed generation ship, albeit with significant modifications to accommodate life support and habitation. The Breakthrough Starshot initiative, announced in 2016, takes a radically different approach. Instead of carrying fuel, Starshot proposes using ground-based lasers to push lightweight spacecraft equipped with large, reflective sails. The laser array, potentially located on Earth or in orbit, would beam intense light at the sail, accelerating the craft to 20% of light speed. At that velocity, a probe could reach Alpha Centauri in about 20 years. The advantage is that the spacecraft carries no fuel, dramatically reducing mass. The disadvantages are equally dramatic. Building a laser array powerful enough to accelerate even a tiny probe requires enormous energy, on the order of hundreds of gigawatts. Keeping the laser precisely focused on a small sail over millions of kilometers is an immense technical challenge. Scaling this concept up to push a multi-thousand-ton generation ship seems impossible with current or near-future technology. However, Starshot demonstrates creative thinking about propulsion and might inspire hybrid approaches that combine elements of different systems. Antimatter propulsion represents the theoretical pinnacle of rocket efficiency. When matter and antimatter meet, they annihilate completely, converting mass directly into energy according to Einstein's famous equation E equals mc squared. The energy density is unmatched by any other fuel. A single kilogram of antimatter reacting with a kilogram of matter releases energy equivalent to 43 megatons of TNT, or roughly the same as the largest nuclear weapon ever detonated. Harnessing this for propulsion could enable velocities approaching a significant fraction of light speed. The problems are, unfortunately, equally extreme. Antimatter doesn't exist naturally in significant quantities in our region of space. It must be manufactured using particle accelerators, an incredibly energy-intensive process. Current production rates are measured in nanograms per year, and the cost is astronomical, literally millions of dollars per microgram. Even if production could be scaled up, storing antimatter is extraordinarily difficult. It must be kept isolated from all normal matter, typically using magnetic or electric fields in ultra-high vacuum. Any contact with matter results in immediate annihilation. A containment failure on a ship loaded with antimatter could be catastrophic. Additionally, the gamma rays produced by matter-antimatter annihilation are intensely dangerous, requiring heavy shielding that adds mass and reduces efficiency. Despite these challenges, research continues. NASA's Institute for Advanced Concepts has funded studies on antimatter propulsion, exploring concepts like antimatter-catalyzed fusion, where small amounts of antimatter trigger fusion reactions in ordinary fuel. Another concept worth exploring is the Bussard ramjet, proposed by physicist Robert Bussard in 1960. The idea is elegant: use magnetic fields to scoop up hydrogen from interstellar space and funnel it into a fusion reactor. The hydrogen would fuel the ship continuously, eliminating the need to carry fuel. The magnetic scoop would need to be enormous, potentially thousands of kilometers across, to collect enough diffuse interstellar hydrogen. As the ship accelerates, the relative velocity of incoming hydrogen increases, providing more energy for fusion. In theory, a Bussard ramjet could maintain constant acceleration, eventually reaching velocities close to light speed. In practice, numerous problems emerge. Interstellar hydrogen is extremely diffuse, averaging about 1 atom per cubic centimeter. Collecting and compressing it requires enormous magnetic fields, which in turn require tremendous energy. Some calculations suggest that the drag from the magnetic field might exceed the thrust produced by fusion, making the concept unworkable. Furthermore, fusing ordinary hydrogen is much more difficult than fusing deuterium or helium-3. It requires higher temperatures and pressures, which our current fusion technology hasn't achieved even in controlled laboratory conditions. While the Bussard ramjet remains a staple of science fiction, its practical feasibility is doubtful with anything resembling current physics and engineering. Solar sails offer another intriguing option, at least for the initial phase of a journey. A solar sail is a large, lightweight, reflective surface that catches photons from the sun or a laser using their momentum for propulsion. Unlike chemical rockets, solar sails don't require fuel, and they can operate continuously as long as light is available. The acceleration is gentle, but over time, it accumulates. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated solar sail technology in interplanetary space. For a generation ship, a hybrid approach might work. Use solar sails or laser-pushed sails to accelerate while near a star, then switch to onboard propulsion for course corrections and deceleration. The challenge is that sails large enough to push a massive generation ship would be enormous, potentially dozens of kilometers across. Manufacturing, deploying, and maintaining such a structure in space presents significant engineering challenges. Let's talk about the deceleration problem, which is often overlooked in discussions of interstellar travel. Accelerating to high velocity is only half the journey. You also need to slow down when you arrive, unless you plan to zip past your destination at relativistic speeds. If you're carrying fuel, you need roughly as much fuel to decelerate as to accelerate, which doubles your fuel requirements. This is the tyranny of the rocket equation at work again. Some concepts propose using the destination star's light for deceleration, deploying a solar sail or magnetic sail as you approach. Others suggest aerobraking, using the outer atmosphere of a gas giant or even a terrestrial planet to slow down. This is risky and requires extraordinary precision, but it could save enormous amounts of fuel. Another option is to send a laser array ahead of the ship, or construct one at the destination star using robotic precursors to decelerate the ship with light pressure. Each approach has trade-offs between complexity, risk, and resource requirements. Time dilation, a consequence of Einstein's theory of relativity, becomes relevant at velocities above about 10% of light speed. As you approach light speed, time aboard the ship slows down relative to stationary observers. At 50% of light speed, time aboard the ship passes at about 87% of the rate experienced by someone stationary. At 90% of light speed, time passes at about 44% of the normal rate. For the crew, this means the journey takes subjectively less time than it appears to outside observers. A trip that takes 100 years from Earth's perspective might feel like only 50 years to the crew traveling at very high velocity. This could reduce the number of generations needed for the journey, easing some of the genetic and social challenges we discussed. However, it also creates a strange disconnect. The crew becomes increasingly separated from Earth's timeline. Messages take longer, not just because of light speed delays, but because the crew's clock runs slower. By the time they arrive, centuries or even millennia might have passed on Earth. They could find that Earth has developed faster than light travel and already colonized the destination, or that human civilization has collapsed, or that Earth has simply forgotten about them. This temporal isolation is psychologically profound. The energy requirements for interstellar travel are staggering no matter which propulsion system you choose. Let's put some numbers to this. A generation ship might have a mass of 1 million tons, which is roughly the mass of a large aircraft carrier. To accelerate this to 10% of light speed requires kinetic energy equal to about 4.5 times 10 to the 21st joules. That's roughly the total energy consumption of human civilization for an entire year, all focused on accelerating a single ship. And remember, you need roughly the same energy again to decelerate. If you're using fusion, you'd need to convert mass to energy with near-perfect efficiency, which is far beyond current capabilities. If you're using nuclear pulse propulsion, you'd need thousands of nuclear devices, each contributing a small velocity increment. The sheer scale of energy involved makes interstellar travel one of the most energy-intensive endeavors imaginable. This is why some researchers argue that interstellar travel might not become feasible until humanity has access to stellar-scale energy, perhaps through Dyson swarms or similar megastructures that capture a significant fraction of a star's output. Beyond propulsion, navigation presents its own challenges. Interstellar space isn't empty. It contains dust, gas, and occasional larger particles. At high velocities, even a speck of dust becomes a hypervelocity projectile capable of punching through metal. A grain of sand hitting the ship at 10% of light speed would release energy comparable to a large explosive device. Let's now turn our attention to one of the most fascinating and unsettling aspects of generation ships: the evolution of society and governance over centuries of travel. When you confine thousands of people in a closed environment for multiple generations, you're not just engineering a technical system, you're designing the foundation for an entirely new civilization with its own culture, laws, and social dynamics. The question of governance is immediate and critical. Who makes decisions aboard a generation ship? How do you balance the need for stability and mission success with individual freedom and democratic values? These aren't abstract philosophical questions. They have direct, practical consequences for survival. One approach is technocratic governance, where decisions are made by experts based on technical necessity and mission requirements. Engineers maintain the propulsion system, biologists manage life support, physicians handle health, and so on. This makes sense in a highly technical environment where poor decisions could be catastrophic. However, pure technocracy can become authoritarian. Who decides which technical experts are trustworthy? What happens when technical requirements conflict with human needs or desires? History shows that expertise doesn't automatically confer wisdom or moral authority. Democratic governance offers an alternative, giving all adults aboard a voice in decisions through voting, representatives, or consensus building. Democracy respects human dignity and autonomy, and it can adapt to changing circumstances through the collective wisdom of the population. But democracy can also be slow, contentious, and vulnerable to demagoguery or majority tyranny. In a crisis requiring immediate action, democratic deliberation might be too cumbersome. What if a majority votes for something that threatens the mission or endangers a minority? A hybrid system seems most practical, combining elements of both approaches. Day-to-day technical operations could be managed by qualified experts with clear authority in their domains. Strategic decisions affecting the whole community, allocation of limited resources, social policies, long-term planning could involve broader democratic input. A constitution or foundational charter established before launch would define the boundaries of authority and protect fundamental rights. This charter would need to be robust enough to maintain essential protections, yet flexible enough to adapt to unforeseen circumstances over generations. Succession and continuity present unique challenges. On Earth, governments and institutions persist through time even as individuals come and go. Laws, traditions, and organizational structures provide continuity. Aboard a generation ship, the same principles apply, but the stakes are higher and the environment more fragile. A constitutional crisis or governance failure could spiral into disaster. The initial crew would need to establish not just rules but deep cultural values around the mission, cooperation, and continuity. These values would need to be transmitted carefully to each subsequent generation through education, storytelling, rituals, and communal identity. Education becomes absolutely central to the mission's success. Each generation must be educated not just in technical skills necessary for ship operations, but also in the history, purpose, and values of the mission. Children need to understand why they're aboard this ship, where they came from, where they're going, and why it matters. This education must be compelling enough to give each generation a sense of purpose and investment in the mission's success. There's a real risk of generational drift, where successive generations lose connection to the original mission. Imagine being the fourth or fifth generation, born decades into the journey. Earth is a distant memory, mentioned only in historical records and family stories. The destination star is still decades away. Your entire life will be spent in this metal cylinder, doing maintenance and work for a goal you'll never see achieved. Why should you care? What motivates you to continue? This is where intentional cultural design becomes critical. The mission can't rely solely on abstract duty or distant goals. It needs to create meaning in the present. Art, music, storytelling, sports, celebrations, traditions, all of these create immediate meaning and community bonds. A rich cultural life makes the journey itself worthwhile, not just the destination. Some designers propose creating a culture of the journey, where the voyage itself is celebrated as humanity's greatest adventure. The crew aren't just travelers waiting to arrive, they're explorers, pioneers, the vanguard of human civilization extending beyond our solar system. Religious or philosophical frameworks might naturally emerge or be deliberately fostered to provide meaning. Throughout human history, religion has helped people cope with uncertainty, find purpose, and build community. Aboard a generation ship, existing Earth religions might persist, evolve, or give way to new belief systems. The ship itself might become sacred, the journey a pilgrimage, the destination a promised land. Mission designers would need to consider carefully whether to encourage, discourage, or remain neutral toward religious development. Religious communities can provide powerful social cohesion and moral frameworks, but religious conflict can also be destructive, especially in a confined space where escape is impossible. The role of history and memory is profound. The crew would need access to extensive records of Earth, its history, cultures, sciences, arts, and natural environment. This serves multiple purposes. It maintains connection to human heritage and identity. It provides knowledge that might be useful at the destination. It offers psychological comfort and cultural richness during the journey. However, as generations pass, Earth might feel increasingly mythological rather than real. Children who've never seen a blue sky or breathed unfiltered air might struggle to relate to Earth's history. The ship becomes their reality, their entire universe. This raises questions about identity. Are the ship's inhabitants still human in the traditional sense, or do they become something new, a distinct culture or even subspecies adapted to space? Decades or centuries of life in reduced gravity, controlled environments, and genetic isolation would inevitably lead to biological and cultural divergence. They might develop different physical characteristics, different social norms, different ways of thinking. By the time they arrive at the destination, they might be significantly different from the humans who remained on Earth. Let's talk about law and justice aboard a generation ship. What happens when someone commits a crime? On Earth, we have prisons, fines, community service, rehabilitation programs. Aboard a ship, options are limited. You can't imprison someone for years without consuming precious resources. You certainly can't exile them, there's nowhere to go. Some crimes might threaten the entire mission and everyone aboard. Minor offenses could be handled through restorative justice, where offenders make amends to victims and the community. Community service, mandatory counseling, or temporary restrictions on privileges might address moderate offenses. But what about serious crimes like murder, sabotage, or violent assault. The death penalty might seem appealing from a resource standpoint, but it raises profound ethical issues. Is it right to kill someone when the community is so small that every individual matters? What if the person has essential skills? What if they're innocent and you make a mistake? Some have proposed cryogenic suspension as an alternative, essentially freezing the offender until arrival, when they can be judged by the new colony's authorities with more resources and options. This is humane in avoiding execution, but raises questions about long-term storage, resource consumption, and whether it's truly just to postpone judgment for decades. Prevention is better than punishment. Careful psychological screening before launch, strong community bonds, mental health support, and a culture that emphasizes cooperation could minimize criminal behavior. But you can't eliminate it entirely. Humans are complex, and closed environments can create psychological stress that manifests in destructive ways. Conflict resolution mechanisms need to be robust and trusted. Mediation, arbitration, and community councils could handle disputes before they escalate. The society would need to cultivate values of patience, forgiveness, and collective responsibility. In a small community where everyone depends on everyone else, grudges and feuds are luxuries no one can afford. Let's consider family structures and relationships aboard the ship. On Earth, families take many forms across cultures: nuclear families, extended families, communal child-rearing, and so on. Aboard a generation ship, family structures might need to be deliberately designed to serve both individual well-being and mission success. Children would need to be educated in ship operations, sciences, and maintenance from a young age, creating an apprenticeship culture where knowledge is passed down directly. Family units provide emotional support and stability, which is crucial for mental health in a confined environment. However, traditional family structures could also create problems. What if a family unit becomes dysfunctional or abusive? In a small community, there's no escape. Social services, counseling, and intervention systems would be essential. Romantic relationships and mate selection present interesting considerations. In a limited population, romantic options are finite. What happens if the population develops strong preferences that lead to many people remaining single or unhappy? What if someone falls in love with someone already in a committed relationship? These scenarios could create social tensions. Some mission designs propose more communal or flexible relationship structures, where romantic exclusivity is less emphasized and child-rearing is shared more broadly. This could reduce jealousy and increase social bonding. However, it also challenges deeply ingrained cultural and possibly biological preferences for pair bonding. There's no one-size-fits-all solution, and the community would need to navigate these issues with sensitivity and flexibility. The birth rate would need to be carefully managed to maintain stable population size. Too many births strain resources and life support. Too few births risk genetic bottlenecks and eventual population collapse. This could involve social incentives, family planning education, or potentially reproductive quotas. The ethics of reproductive control are controversial. Does the collective need for mission success override individual reproductive freedom? This is one of the most difficult ethical questions the mission would face. One intriguing solution is to tie reproductive rights to life stages or social contributions. Perhaps individuals earn the right to have children by completing certain education or service requirements. This ensures that parents are prepared and invested while respecting reproductive autonomy to some degree. But it also creates a hierarchy where reproductive capacity becomes a privilege rather than a right, which many would find deeply troubling. Another consideration is genetic diversity management. With a small founding population, genetics must be carefully monitored across generations to avoid inbreeding and maintain health. This might involve genetic counseling or even arranged partnerships based on genetic compatibility. How much authority should mission planners have over something as personal as whom you partner with? These questions don't have easy answers, and different cultures might approach them differently. Now let's talk about work and economy aboard the ship. Everyone would need to contribute to the ship's operation and maintenance. There's no room for passengers. Everyone must pull their weight. But how do you organize labor? How do you distribute resources? A centrally planned economy makes sense in such a controlled environment. Essential tasks, maintaining life support, propulsion, medical care, food production, get assigned based on skills and necessity. Everyone receives equal access to resources like food, water, living space, and medical care. This eliminates inequality and ensures that essential work gets done. However, pure central planning can be inflexible and fail to account for individual preferences, talents, and innovations. Some degree of personal choice and autonomy makes people happier and more productive. Perhaps people choose their specializations from available options, and scheduling allows flexibility where possible. Currency might not exist in the traditional sense. What would you buy? Everything necessary for survival is provided, and there's no external trade. However, some form of credits or exchange system might emerge for non-essential goods or services, artwork, entertainment, personal items, or favors. This would allow personal expression and create a sense of normalcy. Status and recognition could replace material wealth as markers of achievement. Those who excel in their work or contribute innovations might receive public recognition, special privileges, or commemorative honors. This satisfies the human need for acknowledgement and achievement without creating dangerous inequalities. Leisure and recreation are essential, not luxuries. People need downtime to relax, socialize, and pursue personal interests. The ship would need recreational facilities, gyms, sports areas, arts and crafts workshops, theaters, libraries, and communal spaces. Virtual reality could provide escapes into simulated natural environments, historical settings, or fantastical worlds. This technology would be invaluable for psychological health, providing sensory variety and mental stimulation that the ship's physical environment cannot. Innovation and adaptation are crucial for long-term survival. The ship's systems will age and fail in ways that designers couldn't perfectly anticipate. The crew needs not just to maintain systems but to improve them, repair them creatively, and adapt to changing circumstances. This requires a culture that values problem-solving, creativity, and education. Scientific research, engineering development, and artistic expression should be encouraged and celebrated. The ship might maintain laboratories and workshops where crew members can experiment, invent, and learn. Children would be educated not just to follow procedures, but to think critically and solve problems. The mission's success depends on every generation being as capable and innovative as the one before, ideally more so. Communication with Earth adds another layer of complexity. Initially, messages would travel at light speed, meaning conversations have increasingly long delays as the ship moves farther away. A message to Proxima Centauri takes over 4 years each way. By the time you send a question and receive an answer, nearly a decade has passed. This makes real-time conversation impossible, but periodic updates, news, scientific data, and cultural exchanges could continue. Earth's messages would provide connection to humanity's broader civilization, offering new scientific discoveries, cultural developments, and moral support. However, as decades pass and Earth develops while the ship remains in transit, the divergence between the two societies would grow. Earth's messages might eventually feel alien or irrelevant to the ship's inhabitants, and there's always the possibility that communication simply stops. Earth could face catastrophe, decide the mission is no longer worth supporting, or simply move on. This brings us to the haunting question. What if the ship arrives only to find that Earth has developed faster than light travel and already colonized the destination? Or what if they arrive to silence, with no messages from Earth for decades, uncertain whether human civilization still exists? These scenarios would be psychologically devastating, yet they're real possibilities that the crew would need to prepare for mentally and emotionally. Now let's explore one of the most fundamental challenges facing generation ships, keeping humans biologically healthy and viable across centuries of space travel. The human body evolved over millions of years to function in Earth's specific environment. 1 g of gravity, a protective atmosphere, a magnetic field shielding us from radiation, and exposure to countless microorganisms that have shaped our immune systems. Remove all of that, confine people to an artificial environment, and biology starts doing unexpected things. We've already touched on radiation and its genetic effects, but let's go deeper into the medical infrastructure required aboard a generation ship. The crew would need a complete medical system capable of handling everything from routine care to complex surgeries, all without the ability to evacuate patients to specialized facilities or consult with Earth-based experts in real time. Basic healthcare, treating injuries, infections, delivering babies, managing chronic conditions, would require doctors, nurses, and medical technicians trained in multiple specialties. On Earth, medicine has become increasingly specialized. A cardiologist doesn't perform brain surgery, and a pediatrician doesn't treat geriatric patients. Aboard a generation ship, medical personnel would need to be generalists, capable of handling diverse situations with limited resources. This represents a return to earlier forms of medicine, where country doctors handled everything from childbirth to setting broken bones to treating infections. Medical knowledge would need to be preserved meticulously across generations. Extensive medical databases, textbooks, video tutorials, and ideally some form of artificial intelligence medical assistant would help maintain expertise. Medical education would be continuous and comprehensive, with experienced practitioners training the next generation through apprenticeships and hands-on practice. Surgical facilities would need to be sophisticated despite space and resource constraints. Operating rooms with sterile environments, anesthesia equipment, imaging systems like X-rays or ultrasound, and a full range of surgical instruments would be essential. But here's a challenge. Many medical supplies are single-use on Earth for safety and sterility reasons. Aboard a generation ship, single-use items are a luxury. Everything would need to be sterilizable and reusable, or manufactured aboard using 3D printing or other techniques. Pharmaceutical production presents another major challenge. Medications have shelf lives, typically measured in years, not centuries. The ship would need to manufacture medicines aboard using chemical synthesis or biological production methods. This requires raw materials, laboratory equipment, and personnel trained in pharmaceutical chemistry and quality control. Some medications are complex biological molecules produced by genetically modified organisms, insulin, antibodies, vaccines. The ship would need to maintain cultures of these organisms or the capability to recreate them from genetic databases. Let's talk about genetics in more detail. With a founding population of perhaps 500 to a few thousand individuals, genetic diversity is limited compared to Earth's billions. Every human carries dozens of harmful, recessive mutations that normally don't cause problems because we inherit functional copies from one or both parents. In a small, isolated population, the probability of two people carrying the same harmful mutation having children together increases dramatically. Over generations, these recessive conditions become more common. One study using population genetic simulations found that with a founding population of 500, genetic diversity would decline by approximately 1 to 2% per generation due to random genetic drift, even with perfect random mating. After 50 generations, roughly 1,200 years, genetic diversity could drop by 50 to 75%. This doesn't necessarily mean genetic catastrophe, but it increases vulnerability to disease and reduces adaptability. Several strategies could mitigate genetic decline. Genetic screening of the founding population could deliberately maximize diversity, selecting individuals with complementary genetic profiles. Before departure, the crew's complete genomes would be sequenced and analyzed. During the journey, genetic counseling could help people choose partners who are genetically dissimilar, reducing the likelihood of harmful recessive pairings. This isn't quite arranged marriage, but it does involve guidance and social pressure around one of the most personal decisions humans make. More controversially, the mission might employ genetic engineering or gene therapy to correct harmful mutations before they're passed to offspring. CRISPR and related technologies already allow precise editing of human DNA. By the time a generation ship launches, these tools will likely be far more advanced. Ethical debates about designer babies and human genetic modification would need to be resolved before departure. Once underway, the isolated population might develop its own evolving ethics around genetic intervention, potentially diverging from Earth's values. Frozen genetic material, sperm, eggs, and embryos from a diverse population could provide a genetic reserve. If the population's diversity drops dangerously low, new individuals could be conceived using this stored material, introducing fresh genetic variation. This is technically feasible with current cryopreservation technology. However, it requires reliable freezer systems operating for centuries, and it raises questions about identity and parenthood. Would children conceived from century-old genetic material be full members of the community, or would they be seen as outsiders? Another fascinating possibility is carrying frozen tissue samples or complete genomes from thousands of Earth humans, preserved as digital data. At the destination, these could be used to reconstitute genetic diversity through cloning or synthetic biology. This is speculative, but not impossible with advanced biotechnology. It would essentially allow the small crew to carry the genetic heritage of a much larger population, reconstituting it upon arrival. Disease management is another critical concern. Infectious diseases have shaped human history, from the Black Death to smallpox to COVID-19. Aboard a generation ship, the disease environment would be unique. The founding crew would bring whatever microorganisms they carry, bacteria, viruses, fungi, in their bodies and on their belongings. In theory, the enclosed environment could be carefully sterilized, eliminating many pathogens. However, eliminating all microorganisms would be counterproductive and probably impossible. Humans have microbiomes, complex communities of bacteria, fungi, and viruses living on our skin, in our digestive systems, and throughout our bodies. These microorganisms are essential for health, aiding digestion, training our immune systems, and protecting against harmful pathogens. The ship's crew would carry their microbiomes with them, and these would evolve in the ship's environment over time. Some diseases might disappear quickly in the closed environment. Diseases that require large populations to persist, like measles, which needs constant transmission among susceptible individuals, would die out within months or years. Other diseases, especially those with chronic or latent infections, would persist. Herpes viruses, for example, remain dormant in infected individuals for life, occasionally reactivating. Tuberculosis can remain latent for decades. New diseases could also emerge. Bacteria and viruses evolve rapidly, especially when exposed to new environments or selective pressures. Antibiotic-resistant bacteria are a current concern on Earth. Aboard a ship, where antibiotics would be used carefully but inevitably, resistance could develop quickly. The crew would need robust public health measures, quarantine protocols, hygiene standards, vaccination programs to prevent outbreaks from becoming catastrophic. Interestingly, the ship's small population could make disease control easier in some ways. Contact tracing is straightforward when everyone knows everyone else. Quarantine is feasible when the entire population is already contained. But it also means a single outbreak could affect a significant portion of the population, potentially crippling essential operations. Mental health deserves focused attention as a medical concern. Depression, anxiety, schizophrenia, bipolar disorder, PTSD, and other conditions affect significant percentages of Earth's population. There's no reason to think they'd disappear in space. In fact, the stress and confinement might exacerbate them. The ship would need psychiatrists, psychologists, therapists, and counselors. Mental health care would need to be destigmatized and normalized as essential for everyone, not just those in crisis. Psychiatric medications would need to be available, manufactured aboard the ship, just like other pharmaceuticals. Non-pharmaceutical treatments, cognitive behavioral therapy, mindfulness practices, support groups, even carefully designed environmental interventions like access to nature simulations or communal activities would be equally important. One particularly difficult question is what to do about individuals who become severely mentally ill in ways that threaten themselves or others. On Earth, psychiatric hospitalization and long-term care facilities exist for such cases. Aboard a ship, space and resources for long-term psychiatric care are limited. Would the community be able to provide adequate, humane care? Or would difficult decisions need to be made about risk management and resource allocation? These are uncomfortable questions without easy answers. Let's talk about pregnancy and childbirth. Having babies in space isn't something humans have done yet, at least not beyond early embryonic development in experiments. We don't fully understand how microgravity or reduced gravity affects fetal development, though animal studies suggest potential problems with bone formation, muscle development, and sensory systems. Generation ships would use rotating sections to create artificial gravity, which should mitigate most of these concerns if the rotation provides close to 1G. However, pregnancies would need to be carefully monitored with ultrasound and other diagnostics to catch any developmental abnormalities early. Prenatal care would be comprehensive and mandatory. Childbirth itself could be complicated in artificial gravity if it's not exactly 1G. Labor and delivery are physically demanding processes that evolved in Earth's gravity. Midwives and obstetricians would need training specific to the ship's environment. Medical facilities would include maternity wards equipped for both routine and complicated deliveries, including cesarean sections. Infant and child health would require special attention. Children are more vulnerable to environmental stressors than adults. Their immune systems are still developing, they're growing rapidly, and they're more sensitive to nutritional deficiencies or toxins. Pediatric care would need to address unique challenges like ensuring proper bone development in artificial gravity, managing the psychological effects of growing up in confinement, and providing adequate nutrition during growth spurts. Elderly care is equally important. As people age, they develop chronic conditions, cardiovascular disease, diabetes, arthritis, dementia. The ship would need geriatric specialists and facilities for elder care. In a society where every person matters, caring for the elderly isn't just compassionate. It's essential for maintaining social cohesion and honoring the contributions of previous generations. However, resource constraints create ethical dilemmas. If an elderly person requires extensive medical resources to keep alive, but those resources are needed for younger people or essential operations, what should be done? On Earth, we often avoid these questions through resource abundance. But aboard a ship, they're unavoidable. The society would need to develop ethical frameworks around end-of-life care, potentially including acceptance of natural death rather than extreme life-prolonging interventions. Palliative care and death with dignity would be important concepts. When someone is dying and nothing more can be done medically, comfort care, pain management, and psychological support for both the dying person and their loved ones become paramount. The ship would need hospice facilities or protocols, and the culture would need to develop healthy attitudes toward death as a natural part of life, not something to be fought at all costs. Death and burial present practical challenges. On Earth, we bury or cremate the dead. Aboard a ship, burial in the traditional sense is impossible. There's no ground. Cremation uses energy. What should be done with bodies? Some propose a recycling approach where bodies are broken down biologically and their component materials returned to the ship's biosphere. This might sound disturbing, but it's essentially what happens naturally on Earth through decomposition. Everything is recycled. Alternatively, bodies could be preserved in some way as a memorial or ejected into space in a funerary ritual. Different cultures might develop different practices. The important thing is that death is handled in a way that provides psychological closure for the living while managing the practical realities of limited space and resources. Physical fitness and exercise would be mandatory for health in artificial gravity. Even with rotation creating gravity-like conditions, the environment is still artificial. The Coriolis effect, caused by rotation, creates subtle differences in how moving objects behave. This can affect balance and coordination, especially initially. Regular exercise would help people adapt and maintain bone density, muscle mass, and cardiovascular health. The ship would need gyms, sports facilities, and possibly swimming pools if water can be spared. Physical activity also provides mental health benefits, stress relief, and social opportunities through team sports or group exercise. Making fitness a cultural value integrated into daily routines would help ensure everyone remains healthy. Nutrition requires careful management. We've discussed closed-loop life support and agriculture, but let's focus on the nutritional aspects. Humans require not just calories, but a complex array of macro and micronutrients, proteins, fats, carbohydrates, vitamins, minerals, and trace elements. Deficiencies can cause serious health problems. Vitamin C deficiency causes scurvy. Vitamin D deficiency affects bone health. Iron deficiency causes anemia. B vitamins are essential for neurological function. A diverse diet with multiple food sources helps ensure adequate nutrition. However, aboard a ship, dietary variety is limited. The crew would likely eat a repetitive diet based on whatever crops and protein sources can be grown efficiently. Nutritional supplements might be necessary to prevent deficiencies. These supplements would need to be manufactured aboard, adding to the list of required industrial capabilities. Food culture and cuisine would evolve in interesting ways. Traditional Earth cuisines require ingredients that might not be available. How do you make pasta without wheat, or sushi without ocean fish, or curry without certain spices? The crew would need to develop new culinary traditions based on available ingredients, creating a unique food culture that's both connected to Earth's heritage and distinctly their own. Taste fatigue is a real phenomenon where eating the same foods repeatedly makes them less appealing, even if they're nutritionally adequate. Variety in preparation, seasoning, and presentation can help combat this. Skilled cooks and food scientists would be valuable crew members, finding creative ways to make limited ingredients interesting and appealing. Food is more than fuel, it's culture, comfort, and pleasure. Maintaining good food quality and variety contributes significantly to psychological well-being. Let's address substance abuse, addiction, and intoxication. Humans have used psychoactive substances for thousands of years: alcohol, tobacco, cannabis, opiates, stimulants. These substances serve various purposes: social bonding, stress relief, recreation, spiritual experiences. They also cause problems: addiction, health damage, impaired judgment, and social disruption. What policy should a generation ship have regarding intoxicants? A total ban might prevent problems, but could also create a black market, resentment, and cultural tension. People might attempt to produce substances illicitly, potentially creating dangerous situations. Allowing controlled use of certain substances, perhaps alcohol produced from agricultural waste or specific plants grown for the purpose, might be safer. However, production uses resources and creates health and safety risks. The society would need to balance individual freedom with collective safety. Clear policies, education about risks, and support systems for those who develop problems would be essential. Addiction treatment would need to be available and effective. Given the closed environment, someone with a severe substance abuse problem can't simply be isolated. They're part of the community and must be helped to recover. Emergency medicine deserves special mention. Accidents will happen: industrial accidents, fires, pressure failures, radiation exposure, traumatic injuries. The ship's medical team needs to be prepared for emergencies. Trauma surgery, burn treatment, toxicology, emergency response protocols, and rapid response teams would all be necessary. Training would include regular drills and simulations to keep skills sharp. If this disturbed you, click this video on the screen now. I reveal the truly terrifying side of generation ships, mutinies, madness, and moral nightmares you won't believe.